Hello and welcome to another episode of This is Automation Live. I'm your host, Corey Dallas, and we are very happy to have you with us today. So today we're going to be talking about Ethernet Powerlink. And Ethernet Powerlink is, at its simplest level, just a field bus, but it has much more than that wrapped up inside of it. So it is an Ethernet-based field bus, obviously designed for use in an industrial environment. So it's fast and it's real time. And we'll talk about all of those things and how Powerlink works in just a minute. But I wanted to go ahead and tease out the episode for next week. So we'll be talking about some of the basic concepts of machine vision. So machine vision is obviously a somewhat complicated topic, and there's a lot of specific technologies that we could talk about, but I wanted to take some time to just go through some of the basics, some of the fundamentals, so that you have kind of that basic level of understanding that you need to move forward into understanding some of those more advanced concepts. So if you're someone who's new to machine vision, I would definitely recommend tuning into that episode, or maybe you just need to brush up on some of the basics, fundamentals. You just need a refresher. That's definitely going to be a good one to check out. So make sure you set up notifications for that one so that you can get it. And if you haven't already, go ahead and just subscribe to the channel. That way, anytime we post a new video, whether it's a live stream or a podcast episode or something else, you'll go ahead and get a notification for that. You can go check it out. All right, so let's go ahead and start our discussion on Ethernet Powerlink. So when we talk about Ethernet Powerlink, one of the first things that you'll see as far as terminology is this concept of managing node and controlled node. So this concept is not very different from what you may be familiar with other protocols as a master and a slave. Essentially, the managing node is basically responsible for controlling the traffic in the network. So we'll talk about some of those specific messages that go back and forth between the managing node and the controlled node, but these are just some terms that we'll be using going forward. So each Powerlink network only has a single managing node. It is somewhat arbitrary. It doesn't, in many ways doesn't really matter which node is the managing node, but there can be only one, so to speak. And the controlled nodes are basically taking commands from the managing node as far as when they can speak, when they're allowed to send messages out on the network. So the maybe best place to start is an introduction to the Powerlink cycle. So Powerlink has cycles, and there are different phases of those, different steps that we go through basically at a regular interval. So there's kind of two parts of that, which we'll talk about in more detail. The first part of that is called the Isochronous phase. This is the kind of real-time, time-sensitive component. So there's some special things happening there that we'll talk about. And then the second part of it is the asynchronous phase. So the asynchronous phase is where that non-time critical information happens. Again, we'll get into some of the details of that, but just to give you some contextual basics. So again, we talked about managing node and controlled node. The start of every Powerlink cycle is basically the managing node sending this start of cycle command. So when you see that SOC on the arrow, that stands for start of cycle. This is basically just a synchronization. So that start of cycle message gets sent to all of the controlled nodes, so that all of the controlled nodes are working basically on the same clock as the managing node and all the other controlled nodes in the system. And we'll look at this in the context of, a one-to-one managing node, controlled node for now, just for simplicity's sake. But then in just a minute, we'll look at how that looks with multiple controlled nodes in the system, which would be a more typical application. Okay, so after that start of cycle, the managing node is going to send what is called a pull request message. So kind of the key to Powerlink, how it works, how it maintains its real-time communication, is that the managing node is always kind of managing the traffic in the system. So as opposed to like standard Ethernet implementation where you could have multiple nodes talking at the same time, and there may need to be some arbitration or something like that happening, the managing node is dictating when the controlled node can send messages and which controlled node can send messages at any given time. So that's one of the key things. So how that happens is with this pull request message. So that pull request goes to this controlled node in this instance, and Once the controlled node receives that message, it will send a pull response. So the pull response message is what the controlled node sends back out onto the network. So one of the things we'll talk about in a little bit more detail later on is that Powerlink uses a broadcast principle. So this pull response message will not just go back to the managing node and then the managing node sends it back out. That's actually not what happens. That pull response gets broadcast to the entire network. Okay, so that has some distinct advantages that we can get into in just a minute. Okay, so what about when we have multiple controlled nodes? How does that work? It's very much the exact same thing. So again, we send that start of cycle command to all of our controlled nodes. From there, we would then again do our pull request and then see a pull response from that first controlled node. Then we would go to the second controlled node, request, response, and so on and so forth, request, response, until all of the controlled nodes have had a time to speak, so to say. So if we look at the entire Powerlink cycle, this is pretty much what it looks like. This is what we just broke down. The green squares on the top would be the managing nodes messages, and the blue squares on the bottom would be from the controlled node. So again, that SOC is the first thing that happens, start of cycle. Then the managing node sends a pull request to the first controlled node in the system, gets a response, so on and so forth, to in many of controlled nodes. And after that, that completes what we call the isochronous phase of a Powerlink cycle. Now I mentioned that there's also an asynchronous phase. So similar to the SOC message, there's an SOA message, which is basically just the start of asynchronous. And once that start of asynchronous message goes out, then all of the asynchronous data in the system gets sent out. So this could be anything from standard Ethernet traffic. It could be an IP camera streaming some images, really any kind of standard Ethernet traffic or other data that isn't time sensitive. Okay, so one of the things that we just talked about was the concept of broadcast. So in a broadcast network like Powerlink, the messages are sent out to every node on the system. So we're not routing our messages to a specific node. Even when we are getting a pull response from a controlled node, it's not going back to the managing node, and then the managing node figures out what to do with it. It actually sends that out to the entire network. So that's what we call that broadcast mechanism, because it's broadcasting its messages out to everybody. So this is actually a really good thing in a lot of ways, because this means that a controlled node can communicate data directly to other controlled nodes without having to go back to the managing node. So we call this direct cross traffic, and it's a nice little feature of Powerlink. So again, maybe where you would see this is in a system with some tight synchronization requirements or something like that. When you're using this broadcast mechanism to have direct cross traffic, so direct cross communication between controlled nodes, it can actually shorten the amount of time that it takes to communicate with those different nodes. So, motion control or something like that, this can be a really strong advantage. Okay, so the next thing I wanted to talk about is multiplexing. So again, we'll see this Powerlink cycle over and over again. So that's kind of why we started with that. Multiplexing is a manipulation of the standard Powerlink cycle. So again, with the standard Powerlink cycle, we have the start of cycle command, pull request, pull response, pull request, pull response, and then we start the whole thing over again, exactly the same. With multiplexing, what we can do is actually dedicate a certain amount of time slots to be shared between different low priority controlled nodes. So in this example that we're looking at, let's say that the red text indicates are really time critical. We need it every single Powerlink cycle. We need this data for controlled node 1. But in the blue text, maybe this is not as time sensitive for whatever reason. What we can do is say, okay, that second time slot in this example, that second time slot, we want to allow that to be occupied by multiple low priority controlled nodes. So in the first Powerlink cycle, we'll have our start of cycle, pull request and pull response for controlled node 1, which is our high priority one, and then pull request and pull response for controlled node 2, which is one of our low priority ones. Then on the second cycle, we would see the same thing: start of cycle, request and response for our controlled node 1, which is that high priority one. But this time, instead of having controlled node 2, we would do controlled node 3. Okay, so what this allows us to do is to break up our Powerlink cycle across multiple different low priority controlled nodes. They can share the same time slot, and we can fit more data into a given Powerlink cycle. Okay, so this is a nice feature. This is a simplified model of it. Typically, you would have more than just 2 request responses in a single cycle. But especially if there's really time critical data and we need to conserve the amount of data that we're using in each Powerlink cycle, this can be a good way to kind of shift off some of that lower priority data by using this multiplexing feature. All right, asynchronous data, we talked about this a little bit. This comes at the end of every Powerlink cycle, is a dedicated space for any asynchronous data to be communicated. So when we say asynchronous, this basically means that it's non-time sensitive, so it's non-time critical data packets. So again, Powerlink supports standard Ethernet traffic in this asynchronous phase. So that means if you wanted to commute any TCP/IP communications, really anything that you want that would be standard Ethernet, you can actually wrap that up inside of this asynchronous data frame and send that out over your standard Powerlink. So that's really nice. Let's say you again wanted to communicate some standard TCP/IP, but you don't want to have 2 redundant networks, redundant cables. Instead of having an Ethernet cable and then another Ethernet cable for Powerlink, you can actually just combine those together, send that Ethernet data in that asynchronous phase. So really powerful mechanism that allows you to leverage the real-time capabilities of Powerlink where it's needed, but also to leverage standard Ethernet or other asynchronous modes of communication when that data is not as time critical. So you're not really like locking yourself down to only real-time functionality, which is great, but it's only great when you need it. If you don't need it, then there's data limitations and things like that. So this asynchronous phase can be really, really powerful way to expand your application and expand the capabilities of Powerlink. All right, poll response chaining. So poll response chaining is a nice, another nice feature that we see in Powerlink. We talked about, the standard Powerlink cycle is start of cycle, poll request, then poll response, poll request, then poll response, poll request, then poll response. We can actually do something a little bit different. Instead of having a request to every single controlled node in the system, you can actually send out this kind of blanket poll request to all of the controlled nodes and just tell them, hey, this is the time that you have to speak, this is the time that you have to speak, and this is the time that you have to speak. So that way, there's still not going to be any overlaps, but it can save some time because the managing node doesn't have to, after every single poll response, it doesn't have to then issue another pull request. So this can shorten, compress that Powerlink cycle a little bit more if you need to optimize it for any reason. So basically, the way that this works is, again, instead of that individualized pull request to each of the controlled nodes, there's just a single query that goes out to all of the controlled nodes, and then they respond in a sequence. So we send out that pull response chaining request, and then controlled node 1 speaks, controlled node 2 speaks, then controlled node 3, on down to n number of controlled nodes. And then again, at the end, we would then just start our asynchronous phase. So another neat feature for optimizing the Powerlink cycle, if you have, again, really time critical operations, if those microseconds can make a difference, which they often do, this can be a really, really nice feature. Okay, so let's talk about topology. So we've talked about how the Powerlink cycle works, and then some of the nuances of the Powerlink cycle with some of the different things you can do in the asynchronous phase with poll response chaining and some of the other features. Now let's talk about topology. So this one's kind of simple. It's really the same as any standard Ethernet topology. So Powerlink is implemented on top of the Ethernet standard. So it supports the full Ethernet standard, which is great. So what you see here is a couple different topologies. One would be like a line. So on the right-hand side there, it's basically a line of nodes. You may also know this as daisy chaining. So from node 1 to 2, 2 to 3, 3 to 4, so on and so forth. The other thing that you can do is what we call like a tree topology. So more like what you see on the left-hand side. Instead of directly going into each one, there's kind of a routing or tree mechanism where node 1 goes into nodes 1 or 2, 3, 4, and 5, and so on and so forth. So that tree can have multiple different levels of depth. Okay, there's some advantages and disadvantages that we'll talk about to both of those in just a minute when we answer the question, how many nodes can I have in my system, which is a pretty common one. But before we do that, I wanted to talk about some of the physical hardware. So there's some common questions that get asked about Powerlink quite a lot. So I wanted to address those specifically. The first one is you'll see in a lot of Powerlink documentation the recommendation to use a hub. And one of the questions that comes up is, do I have to use a hub or can I use a switch? So for those of you that aren't very familiar with the difference between a hub and a switch, it's pretty similar. They use different layers of the OSI model, which maybe we could talk about in another episode. But basically a hub is a more simple device. So it basically takes packets in and shoots them right back out. There's very little processing that happens inside of a hub. So that makes it really nice for Powerlink, which we'll talk about in just a second. But when we talk about a switch, a switch has, additional capability. It's looking at MAC addresses and things like that to know where to send packets. But the ultimate question is, do I have to use a hub in a Powerlink system? No, you don't. The chart here that we're looking at on the screen is kind of the asterisk to that. So when we look at a hub, I mentioned it's a simpler device as far as what it's actually doing. It's just taking every single packet in and sending it out. So it's more of that kind of broadcast style implementation. So that means that it has really low processing time. Okay, so the delay introduced by hub is something on the order of a half a microsecond to a microsecond typically. And there's some jitter in there on the order of 40 nanoseconds or something like that. So very low delay relatively. When we look at a switch, it can be typically on the order of 4 microseconds or more. So that doesn't seem like a lot. And in many cases it's not, which is why, the answer is no, you don't have to use a hub. You can use a switch, but we have to be careful of what we're looking at here on the screen. So in very time sensitive applications, that 4 microseconds can actually add up quite a bit, especially as you go through multiple different switches or multiple different hubs. So the answer is yes, you can use a switch. No, you don't have to use a hub. But just be aware that there is this impact of timing. And so when you're laying out your system architecture, just know that, we need to consider how this timing is going to affect our system. So, it's the same consideration with cable length. There are delays introduced with cable length that need to be considered. So in those really time critical, motion control applications, it's just something that we want to calculate out and fully understand the impact of. All right, another common question that we see is, can I use standard Ethernet cables? So this is somewhat related to the last question. I want to use just standard hardware. Do I have to use a special Powerlink cable? No, there's nothing really special about a Powerlink cable, actually. It's just a standard Ethernet cable. When you buy a cable that's called a Powerlink cable, it is likely just a shielded industrial grade Ethernet cable. So anything that is industrial and shielded is more than likely going to work. If you're using a type 2 or newer Powerlink system, you can do either a crossover cable or a one-to-one patch style cable. So really no limitations there. Actually all new systems I would say that are being implemented would be type 2, at least right now. You may come across some legacy systems that are this type 1, which doesn't support the auto MTCX to handle the crossover or the one-to-one. So that's maybe the one nuance that you need to be careful of. But in general, you don't need to take any special precautions with your cables other than making sure they're good quality, they're industrial grade, and they're shielded, because you want to make sure that you're protecting it against noise. The other question that we kind of address here is, what is the maximum distance between nodes. Again, there's nothing Powerlink specific about that, which is great since the entire Ethernet standard is implemented within Powerlink. You have a maximum of 100 meters over copper between two Powerlink nodes. So the one caveat there is, with fiber, of course, we could go further. So if you're looking at an application that is more than 100 meters, you can probably still do it with Powerlink. You just need to look at a solution that is not based on copper and maybe is based on fiber optics. All right, so we talked about topology not too long ago, and we looked specifically at a tree or a line topology. A lot of Powerlink devices have these integrated hubs or integrated switches so that you can daisy chain from node to node, which is great. It makes cabling super simple, but there are impacts to your timing. Again, timing is kind of the important thing here, depending on which system you're looking at. So when we answer the question, how many nodes can I have in my system? The addressing limitation is 239 nodes per network. So that doesn't mean that if you have 250, you can't do it. You just have to have separate Powerlink networks. But oftentimes there may be a topology change that could be required to even reach that many nodes. So to clarify what I'm talking about, if we look at the chart on the screen here, there's two lines. There's a red line and a green line. You can see the red line is kind of exponentially growing, and that green line is more linear and also at a much shallower slope. The x-axis there is number of stations, so number of nodes. So we'll 0 on the far left and 25 on the far right, just to give you some context. And the y-axis is time. In microseconds. So starting at 0 and up to 350 at the highest. And that time is the sum of hub delays. So we mentioned every time you go through a hub, so anytime you're daisy chaining, you're going through a hub. Every time you do that, you're introducing some delays. We talked about that earlier on the order of microseconds. Now, when you go through a line topology, those delays get multiplied. Whereas opposed to a tree topology, those delays are spread out linearly instead. So if we were to try to implement 239 nodes in a line topology, we're going to see hub delays, that sum of hub delays get really quite large, and maybe to the point where it may not be viable anymore. And even for a lot of applications where you may see a Powerlink cycle on the order of 400 microseconds, if we've got 25 nodes in a line architecture, now we're introducing hub delays of 350-ish, 325 microseconds. That's almost a full Powerlink cycle. So you can see how this can become pretty important, again, especially in motion control applications where we want those really fast Powerlink cycles and we want to minimize hub delays and jitter and things like that. So again, just a consideration, how many nodes you can have in the system is really a question of A, timing, and B, topology. So, typically a good rule of thumb is to have no more than 10 nodes in a line, and then you would probably want to branch off into, another branch from your tree architecture. So, we don't typically see just like a strict tree architecture. It's usually a tree line kind of hybrid. But again, that 10 hub depth is, about the number that you're going to want to be at so that there's not a big impact on the system. And you can see on the chart here, when we look at the line at 10 nodes, that's about 50 microseconds. Okay, so again, depending on the application, that they may be different, but 10 is a good rule of thumb. All right, so that wraps us up for our quick intro to Powerlink. Hopefully that answers some of your questions as far as how Powerlink works, where you may see it used. Again, just to summarize, one of the key things with Powerlink is its capability to do a really good job in motion control applications because of the direct cross-traffic communication. That's a really strong point of Powerlink. It's also great in those applications where you may need asynchronous data, like standard Ethernet traffic over your field bus line as well. So there are certainly many other viable field bus solutions out there, but Powerlink is a good one. Hopefully this gave you some insight into why you may want to use it, where you may want to use it, and some of the neat features that we see inside of Powerlink. If you have any questions about Powerlink or how to implement it or why you might want to implement it, leave a question in the comments below, and we'll be sure to get back to you on those. Maybe just one more note, common misconception about Powerlink is that, it isn't open source. It actually is open source. There's OpenStacks available. So you can find those on the Ethernet Powerlink standardization group website, which I'll include in the links below. So there are open Powerlink stacks for both managing node and controlled node, which are free to use. So that's really great if you wanted to implement it in your custom hardware or, on your own. But there are also many other third-party solutions out there that support Powerlink. So again, just to recap, we'll be talking about key concepts in machine vision next. So if that sounds like something that's interesting to you, go ahead and subscribe to the channel, hit the little bell icon on the machine vision video, and that way you'll get a notification as soon as we go live, and you can check that one out. If you have any other questions, comments, concerns, please leave a comment below or reach out to me on LinkedIn. We do appreciate all of the likes, shares, subscribes, everything that you guys are doing is much, much appreciated. And that's going to wrap us up for today. So thank you again for joining us for this episode of This is Automation Live, and we will see you next time.